So the question becomes, given an equation of this form, does a solution exist? Now, whether a solution exists or not, and what it means for a solution to exist, because it's possible for a solution to exist even though we can't write it down in closed form. Just because we can't write down the solution doesn't mean there isn't one. Okay, so the question of whether a solution exists or not often depends on the initial conditions. So let's assume initial condition y of t naught equals y naught and y prime of t naught equals, we'll just arbitrarily call this v naught, and that's chosen. I chose v because if y happens to be a position function, then its derivative is a velocity function. But this notation can apply whether or not y is a position function. Y could be any type of function. We could still call the initial value of its derivative v naught if we so choose, and we've chosen to do that here. Now we want to first consider this question geometrically. What does it mean to have a differential equation with initial conditions? Well, geometrically, this simply means that we have a graph of y versus t. We have some coordinate t naught at which the solution function takes the value y naught. In other words, the point y naught, t naught is a point on this graph. That's what it means. To say that y of t naught equals y naught is simply to say that on a graph of y versus t we have the point t naught, y naught. I might have said that backwards a minute ago, but it's t naught, y naught. And we can label that point. So let's just label the coordinates of the point t naught, y naught. Then the condition y prime of t naught equals v naught simply means that the derivative of y, which is going to be the slope of the y versus t curve at the point t naught, is v naught. So at this point it means we have slope v naught. So that if there is a solution curve in the neighborhood of this point, so if there's a solution to the function in the neighborhood of this point, that solution can be represented by a curve which is tangent to the slope line at t naught, y naught. So our solution curve might look something like this. Now, if this does happen to be the solution curve for this equation, then what do we know about the second derivative? Well, since the curve is concave down, we know that the second derivative of our solution function, our y double prime, would be negative at this point. That's not necessarily the case. Whether it's positive or negative depends on the coordinates t naught, y naught, the slope v naught, and the differential equation in a way that we'll see in a minute. So maybe the curve is concave down at near this point. Maybe it's concave up near this point. Maybe there's a kind of a point of inflection where the concavity changes at this point. we don't know, but our initial conditions and our equations are going to tell us. The key idea is that in the equation a of t y double prime plus b of t y prime plus c of t y equals 0, our initial condition tells us, for this initial point, it tells us that y equals y naught when t equals t naught. So we know the value of y if we know the function c of t and the actual value of t naught. We can plug this value in so we can evaluate c of t times y. It's just going to be c of t naught times y naught. So we get c of t naught y naught from this term. Now what do we know about this term? Again, we know that t equals t naught. And what's y prime? Y prime equals v naught. Again, t equals t naught. So this term gives us b of t naught v naught. Now we can see that we're building up the terms of this equation, so let's go ahead and put the equals 0 here. And what do we get here? Well, again, we know that t equals t naught. We don't know what y double prime is. That hasn't been specified. But now we know that a of t naught, y double prime of t naught, plus these terms have to add up to 0. We conclude well, we can solve this for y double prime of t naught. We know this, we know this, we know this. Y double prime of t naught equals, well, it's going to be negative b of t naught v naught minus c of t naught y naught divided by a of t naught. Provided a of t naught is not equal to 0, b of t naught is defined, and c of t naught is defined. Now we don't know what the functions a of t, b of t, and c of t are, so it's entirely possible that when we specify this initial condition, our initial point t naught y naught, it doesn't make any sense because maybe b of t naught isn't even defined. Maybe when we try to substitute t naught in here, we end up with a 0 in the denominator of our function, or we end up with something else that's for some reason undefined for the function b, c, or a. And we also have a non-starter if solving for y double prime of t naught gives us a 0 in the denominator of this expression. And we should mention that a of t naught also has to be defined. It's not sufficient that a of t naught be non-zero. It also has to be something we can compute, something that is defined. When that's the case, if all the conditions are met, then we can find y double prime of t naught, and that's going to allow us to determine the degree of concavity. So that's going to be, when we go back to here, that's going to be our concavity. It's going to tell us how quickly y prime is changing. Y prime, in turn, which is our slope v naught, tells us how quickly the value of the function is changing. And from those two bits of information, we're going to be able to project our solution a little ways forward.